In previous units, we've looked at solving exponential equations. An example of an exponential equation could be 2 to the power of x is equal to 16. We know that 2 to the power of 4 is 16, so we could say that x was equal to 4. With an exponential equation, we have the unknown as the power, so we're looking to solve for x. Another example might be 2 to the power of 3x plus 1 is equal to 8 to the power of 2x. And we looked at solving this particular equation by writing the bases the same. So we'd have 2 to the power of 3x plus 1 is equal to 2 cubed raised to the power of 2x. I know that 8 now is a power of 2, so I can rewrite this and get the bases the same. At this stage we use the rules of indices. A to the power of m raised to the power of n was equal to a to the power of m multiplied by n. So we end up at this stage with 2 to the power of 3x plus 1 is equal to 2 to the power of 6x. If the bases were the same, we could equate now the powers. So we had 3x plus 1 was equal to 6x. Subtracting 3x from both sides, 3x was equal to 1 and x was equal to 1/3. We'll go ahead and check that that value now satisfies the equation and we solved it. So this was now solving an equation where we had the unknown as the power and we could make the bases the same. This is not always going to be the case. In this video we're going to look at solving exponential equations. We're going to look at 3 different types. We're going to look at the type when we have an unknown on one side, an unknown on both sides, and also quadratic equations. So let's start off. We're asked to solve each equation giving our answer to 3 significant figures. So what we have here is 3 to the power of x is equal to 12. Now with this one we've got a couple of different choices. We could now write the log equivalent, and the log equivalent is log to the base 3 of 12 is equal to x. We could go ahead and evaluate this in a calculator. If we just consider now log to the base a of b is equal to c, our exponential equivalent is a to the power of c is equal to b. So we could use this approach. If I did that, I would use a calculator and find my answer and give it to 3 significant figures. So we take now base 3, log to the base 3 of 12, and that will give us x, which is 2.26, correct to 3 significant figures. So x would be equal to 2.26. The alternative approach is to take logs of both sides of the equation. I prefer this particular approach of taking now logs of both sides of the equation, as it's easier to deal with examples when we have unknowns on both sides. So if we do that, we can choose any base. I'm going to use base 10 throughout these calculations. Base 10 is nice and straightforward to use, and it's something that we have on the calculator readily available. So what I'm going to write then is log 3 to the power of x. So this is base 10, and that's going to be equal to log 12. Now log 12 is just a number. It's saying what power is 10 raised by to get 12. At this stage I can use the power law to bring the unknown down, and that's the advantage of using logs to solve these equations. So using the power law, x log 3 is equal to log 12. So all I've got now is some quantity. Log 3 is the power 10 is raised by to get 3. So I want x. X will be equal to log 12 divided by log 3. Don't fall into the trap at this stage of writing log 4. We know that that is not going to be the case. So all I've done in this particular instance is written the following. If we have now log of a to the power of x, we can write this now as x log a. So all I've done is use now the power law, and we've looked at this in previous videos. So in a calculator, I'm going to go ahead and evaluate this. So what we've got then is the following. I've got log, so I'm going to use base 10. Base 10 is just here. So we've got now log 12 divided by log 3. And that's going to give us now 2.26 as we had before. I didn't need to use base 10. I can use any base. ln is the natural log, or base e. So if I use now base e, it really doesn't matter, as long as we're consistent. So this is going to give me exactly the same. I could have used now base, let's put something really stupid in. Let's put 5.24. I'm not sure why we'd want to, but we can do that anyway. So if I now put in here, let's put in 5.24, just to show now that as long as we're consistent, we can just pop that in. That will give us exactly the same. Yet if I change one of these bases, so let's say we had now, I put in 9.24, we can see that that is not going to give us the same answer. So we need to be consistent, but it really doesn't matter. I use base 10 purely because it's easy and it's in the calculator. So let's look at this one right here. Now, of course, we could write this as a log statement. Log to the base 2 of 0.7 is equal to x. Alternatively, we could just take logs of both sides. So log 2 to the power of x is equal to log of 0.7, where log is base 10. Bringing the power down, x log 2. Log 2 is just a number, log 0.7 is just a number. If we consider now, we're going to have x to be a negative number. If x was 1, this would be equal to 2. If x was equal to 0, this would be equal to 1. So if we consider now, we're going to have a negative. So what we'll have is x will be equal to log 0.7 divided by log 2. Later on, when we look at inequalities, we have to be careful, especially if we're divided now by a number between 0 and 1, if we're using base 10 in this particular case. So if we just look at this now, what we've got, let's go ahead and do this. What I'm going to do is just a quick sketch. This is 2 to the power of x. So to get some idea of what's going on here, this is y is equal to 2, y is equal to 2 to the power of x. So if we consider this point right here, we've got 0, 1. With any exponential, we will go through at 0, 1. So 2 to the power of 0 is equal to 1. So we're asking where this is going to be now 0.7, which is just there. So we can see that that's going to give us a negative number. So in the calculator, let's go ahead and do that. So we got log of 0.7 divided by log of 2, and that will now give us minus a half, something around there. So minus now, and we need to give this to 3 significant figures, so that's going to be minus 0.515. So x is going to be equal to minus 0.515, and that is to 3SF. So that kind of makes sense, and let's just check that. Let's go ahead, that looks good, to 3 significant figures. So do have some concept of what's going on, rather than blindly plugging these in. Now with this one, we've got a minus. It really doesn't matter, and we could deal with this a number of different ways. It's entirely up to us. We could just take logs, so let's just go ahead and write log now, and we've got 8 to the power of minus y is equal to log 3. Bringing the power down, minus y log 8 will be equal to log 3. We want to make y the subject, so we'll divide both sides by minus log 8. So we've got log 3 over minus log 8, or if you like, minus log 3 over log 8. And then we would just go ahead and evaluate that. So it's straight through a calculator. Okay, let's move on and look at some others. Now with this one right here, we have 4 to the power of 1/2 x minus 0.3 is equal to 0. So all I'm going to do is rewrite this. And I'm going to write this now as 4 to the power of 1/2 x is equal now to 0.3. Or if we like, we could write 3/10. At this stage, I'm going to take logs of both sides. So we're going to have now log 4 to the power of 1/2 x is equal to log of 3/10, or 0.3. So we've got this right here. Bringing the power down, 1/2 x, so we can write this now as 1/2 x log, and then we'll have now log 4 will be equal to log 3/10, dividing both sides now by log 4. In fact, we can divide both sides if we wanted by 1/2 log 4. You can do it step by step, or we can just say that now x is going to be equal to log of 3/10, and I'll just put this in brackets, divided by now 1/2 log 4. So that's what we end up with. Now you could have just written this as, if you wanted, you could write this now as 2 to the power of x. It's entirely up to you. You can use the rules of indices there. So it's absolutely entirely up to you. So at this stage you could have actually written this now. If we just consider this is 2 squared to the power of 1/2 x is equal to 3/10. So we could have said 2 to the x is equal to 3/10 and then solve that. I don't think you'll be any better off, especially if you're evaluating now to 3 significant figures, but that just gives you some idea on how you can rewrite these. And in later examples we will look at using this particular property. So in this particular case you could have just written this now as the logarithmic equivalent. Log to the base 2 of 3/10 is equal to x, and solved. So nice and straightforward, or we can just go ahead and evaluate this way. So be flexible, and it should make some sense. Okay, let's look at this one right here. This time we have 5 to the power of t plus 3 is equal to 24. So I'm going to write now log, and then we'll have 5 to the power of t plus 3 is equal to log 24. Log 24 is just a number. Bringing the power down, t plus 3, so we have the quantity t plus 3 multiplied by log 5 is equal to log 24. Dividing both sides by log 5. Log 5 is a number, so t plus 3 is equal to log 24 divided by log 5. We're now going to subtract 3 from both sides, so we have log 24 over log 5 minus 3. And again, we would just simply evaluate that on the calculator and give an answer to 3 significant figures. So if we did that, let's do that. So we got log 24 divided by log 5, so log 5, and then we're going to add to that, what have we got, minus 3. So let's subtract the 3 from there, and that gives us negative 1.03, correct to 3 significant figures. So let's think about this. Let's just write this down. So t, all I've done is blindly plug that into the calculator. So we've got now t is equal to negative, let's do that, negative 1.03. So negative 1.03. Is that reasonable? Well, let's have a look at the original equation. I know that 5 to the power of 2 is equal to 25. So if we subtracted 1.03 approximately from the value of 3, that's going to give me something just under 2. 5 to the power of something just under 2 looks pretty good to be 24. So always think to yourself, and of course you can just plug this back in. If you want to, you can just go ahead now. If we do, and let's do this, let's do 5 now to the power of my answer plus 3. This should now give us the 24, as we can see. So just think, is this a reasonable answer? I didn't evaluate this one, but say to yourself, does it look reasonable? Okay, let's move on. Now with this one, all we would simply do is add the quantity now, 3 to the power of 4 plus x to both sides, and go ahead and solve. So this is no different to what we've looked at. So 16 would be equal to 3 to the power of 4 plus x. We would take logs of both sides. Log 16 is equal to log, then we'd have 3 to the power of 4 plus x. We can bring the power down, so we'd have log 16 is equal to the quantity 4 plus x multiplied by log 3. Log 3, remember, is just a number. Dividing both sides by log 3, we've got now log, so we'd have log 16 divided by log 3 is equal to 4 plus x. Subtract 4 from both sides, so we'd have log 16 divided by log 3 minus 4 is equal to x. We would go ahead and evaluate that on a calculator. Okay, let's move on and do now the examples with unknowns on both sides. So if we look at this one right here, we have 5 to the x is equal to 6 to the x minus 1. I can't manipulate these two bases to be a power of one another, or a power of 1. So for example, if we had again 2 and 8, we could do that 2 and 4. If we had 3 and 9, 3 and 27, etc, etc. So what we're going to do is simply now take logs of both sides of this equation. So what we're going to have then is log 5 to the power of x is equal to log, and then we're going to have 6 to the power of x minus 1. I'm going to use the power law and bring the unknown down. We're trying to solve for x. X is now stuck up as the exponent, or now, if you like, the power. So x log 5 will be equal to the quantity x minus 1 log 6. At this stage, I'm just going to expand the brackets, and we're going to end up collecting the terms in x on one side and the constants on the other side. So we got x log 6 minus log 6. Adding log 6 to both sides, log 6 will be equal to x log 6 minus x log 5. We can factor the log 6 will be equal to x log 6 minus log 5. They are just two numbers. Log 6 and log 5 are just two numbers. So all we would do at this stage is simply divide through now by the quantity in the bracket. So we'd have log 6 divided by log 6 minus log 5, and that will give us x. We now go ahead and simply sub that into a calculator and give our answer to 3 significant figures. So if we do that, let's just pop that in. So what we're going to have is the following. So we've got now log 6. So again, I'll use now base e just to show that we really don't need to use base 10 all the time. So we've got log 6 minus now log, and let's put this in, log 5. So let's just put in ln 5, the natural log of 5, and that's going to give us now 9.827 and so on and so forth. So let's just write that in. So that's going to be 9.83. So we've got now x, let's write this here, x is going to be 9.83. Was it 9.83 or 9.84? 9.83, and that's correct to 3 significant figures. So if we look at that now, all we would do is check that that will give us now a reasonably, if we just look at that, that looks pretty good, as now an answer. But again, you can check. Okay, let's do another one. This one right here, we've got now 7 to the power of y plus 2 is equal to 9 to the power of y plus 1. We would do exactly the same. Let's do one that's slightly more interesting. Let's do this one. We've got now 4 to the power of 5 minus x is equal to 11 to the power of 2x minus 1. So taking logs of both sides, we have log 4 to the power now of 5 minus x is equal to log, and we'll have 11, and then we'll have 2x minus 1. We now need to bring the powers down. 5 minus x multiplied by log 4. Log 4, remember, is just a number. 2x minus 1 multiplied by log 11. At this stage, we want to make x the subject. So what I'm going to do, I'll do this the long way around and expand all of this out. 5 log 4 minus x log 4 will be equal to 2x log 11 minus log 11. So I've just expanded the brackets on both sides. So if we now collect up terms in x and the constants, adding log 11 to both sides, 5 log 4 plus log 11, and then I'm going to add x log 4 to both sides. So I've got 2x log 11, and then I'm going to add to that now x, and then we can have log 4. So I can see now that I can factor out the x. If you wanted, you could write this now. If you didn't want the 2x in there, you could have this as log of 11 squared, bringing the 2 up. It's entirely up to you. So what we have then is 5 log 4 plus log 11 will be equal to, and just factoring out the x, we've got x 2 log 11 plus log 4. And at this stage, we're going to divide through by the content of the bracket. So 5 log 4 plus log 11 divided by 2 log 11 plus log 4 is going to be equal to x. And we'd simply go ahead and evaluate that on a calculator and give our answer to 3 significant figures. Again, you could check and see if that was reasonable. Okay, let's move on and look at these ones right here. Now, this is quite nice. We've got 7 to the power of 2x plus 5 is equal to 7 lots of 11 to the power of 3x minus 4. At this stage, what I'm going to do is divide both sides by 7. Now, I don't need to do this. If I take logs of both sides, I could write log of 7 to the power of 2x plus 5 is equal to log, then I could write 7 plus log now of 11 to the power of 3x minus 4 and split it up. What I'm going to do though is just split both sides of this equation by 7. If I do that, all I'm going to do is subtract now a power off here. So what I can write then, and I'll just rewrite this, I'm going to have this as 7 to the power of 2x plus 4 is equal to 11 to the power of 3x minus 4. Dividing both sides by 7, just consider now that we've got 2x plus 5. What this is saying on the left hand side is that we've got 7 to the power of 2x multiplied by 7 to the power of 5 is equal to 7 to the power of 1 multiplied by this quantity here. So if I'm dividing both sides by 7, all I need to do is knock a power off there. And at this stage, we've got a straightforward task. Logs of both sides, log, and then we can have 7 to the power of 2x plus 4 is equal to log, and then we're going to have now 11 to the power of 3x minus 4. Bringing the powers down, 2x plus 4 multiplied by log 7 will be equal to 3x minus 4 multiplied by log 11. Now at this stage, what I'm going to do is just go ahead and do this very quickly. I'm going to now factor. You should expand it, and if you're in an exam, show full workings. So what I'm going to have is x. I'm going to have 3 log 11 minus now, and I'm going to take 2 log 7. So minus 2 log 7, and this is the lazy way round, and that's going to give me now 4 log 7, and then we're going to have plus now 4 log 11. Let's write log, there we go, 4 log 11. So all I'm going to do now to solve for x is simply divide through by the content of the bracket and evaluate that and give my answer to 3 significant figures. So we could say 4 lots of log 7 plus log 11 divided by the quantity. So I've just taken the 4 out. 3 log 11 minus 2 log 7, and that's going to be equal to x. So straight for a calculator, give your answer to 3 significant figures. Okay, let's finish off with this one right here. This one, we've got 3 to the power of 2x is equal to 3 to the power of x minus 1 multiplied by 2 to the power of 4 plus x. I'm going to use the same idea I just did here and divide both sides of this equation now by 3 to the power of x minus 1. So what I've got, I'm going to have now 3 to the power of 2x divided by 3 to the power of x minus 1. We know if we're dividing now with the same base, we subtract the powers. So this is going to be 3 to the power of x plus 1. So 2x minus x is x. Then we've got minus 1, which is going to give us plus 1. And that is going to be equal to 2 to the power of 4 plus x, or we could write x plus 4. At this stage, we have a nice straightforward problem to deal with. We just bring the powers down, so we could write x plus 1 log 3, and this is me doing it very, not really step-by-step-y, x plus 4 log 2, and then we can go ahead and solve. Again, in an exam, you would show full workings. So that gives us a nice example right there. So if you wanted, you could write this now as x. We would have log 3 minus now log 2, and this is factoring well in advance, and that's going to be 4 log 2 minus log 3, and then all we would do is just split now the content of the bracket, for both sides by the content of the bracket. And again, you might even see this as log 16, bringing the power up. So I'm just kind of switching things around just to give you an idea of how things might be written. Highly unlikely that that would happen, but just to give you an idea. So if you're asked to show something, then you can show what's going on. So all we've done is use the rules of indices and then use the skills we have. I would expect you to expand the brackets at this point, collect the terms in x, factor out the x, and then divide through. This is a shortcut. Okay, let's move on. What we're now going to do is move on to quadratic equations. Let's go back and look at the idea, and I'm just going to quickly look at this idea. If we have now a to the power of m raised to the power of n, we get a to the power of m multiplied by n, which is the same as a to the power of n multiplied by m. So what we could do here is as follows. We could write this as a to the power of n raised to the power of m is either equal to a to the power of nm, which is the same nm, which is the same as a to the power of mn. If we just look at these two things, we can see that the way that this can be written differently gives us exactly the same. So for example now, if I had 2 to the power of 3 raised to the power of 2, this gives us now 2 to the power of 6. I could write this now as 2 to the power of 2 raised to the power of 3, which gives us 2 to the power of 6, which gives us 64. So we can see these things are interchangeable. We're going to use this law now to solve quadratics. This is a quadratic equation in 2 to the x. If you're unsure, you can make a substitution. What we need to do as well is, if we're going to now do a substitution, is make sure we substitute back and check that our answer is reasonable. So let's see what we've got here. What I'm going to do is write this now instead of 2 to the power, we're going to write this as 2 to the power of 2x. We're going to write this now as 2 to the power of x squared plus 2 to the power of x, and I'm going to put these in brackets, minus 6 is equal to 0. Now at this stage, if you're not confident, what we can say is now let p be equal to 2 to the x. We now have p squared plus p minus 6 is equal to 0. That's a quadratic equation in the form ap squared plus bp plus c is equal to 0. That factors p plus 3, p minus 2 is equal to 0. So we can see that p would be equal to minus 3 or p would be equal to 2. We must now write back that p is equal to 2 to the x. Therefore, we've got two different situations. We've got 2 to the x equal to minus 3. Now that can never happen. Or we've got 2 to the x equal to 2. If we think 2 to the x is equal to 2, then x is equal to 1. Not a valid solution here. So quite clearly not valid. Again, if we graph this, the question is, where is 2 to the power of x equal to minus 3? The answer is nowhere, as we have an asymptote on the x-axis. So 2 to any power will never be a negative number, and this is our graph of y equals 2 to the x. So what this is saying is, where is this equal to minus 3? So we need to be very careful. Let's just put that line there. The answer is nowhere. So that one's done. So if you're going to make a substitution, go ahead. Alternatively, you could just factor this. If you're confident to factor this, you could say that that was 2 to the x plus 3 multiplied by 2 to the x, and then we'd have now minus 2 is equal to 0. If you expand this out, we're going to get 2 to the 2x. We add the powers. Minus 2 lots of 2 to the x plus 3 lots of 2 to the x minus 6. So if you're confident, you can use that particular method. Okay, so let's go ahead and do another one of these. So in the first one, we had a quadratic in 2 to the x. We now have a quadratic in 3 to the x. So if we consider what we could do here, we could write this now as 3 to the x, which we're going to square. These things are the same. Just consider now that this is a to the m raised to the n. That's what we get. Minus 5 lots now of 3 to the power of x plus 4 is equal to 0. So if we want, we can let p be equal to 3 to the x, if you don't want to factor it now as 3 to the x. So we have now p squared minus 5p, and then we're going to get plus 4 is equal to 0. So factoring, we'll have p minus 1, we'll have p minus 4, and then that will be equal to 0. So at this stage, we can say that p is equal to 1 or p is equal to 4. Do not leave your answer as p is equal to 1 or 4. Therefore, we can say 3 to the x is equal to 1 or 3 to the x is equal to 4. Let's deal with this one. We can see, therefore, from here now that x would be equal to 0. 3 to the 0 is 1. This one we need to solve. So what we can do is take logs of both sides. So we can say now log 3 to the x is equal to log 4. Bringing the power down, x log 3 is equal to log 4. So x will be equal to log 4 over log 3, and we would give our answer to 3 significant figures. And this is exactly what we looked at in the past. So that's what we've got. You could, of course, just write this now as log to the base 3 of 4 is equal to x and use the exponential logarithmic equivalence and solve. So that's what we get. And you just evaluate this now on a calculator. So we'd have now log 4 divided by log 3. And that would give us that numeric answer of 1.26. So we'll say 1.26, let's just write this, 1.26, and that now is to 3 significant figures. So we've got a quadratic in 3 to the x. Let's look at this one quickly. We can just rearrange this. We've got a quadratic in 5 to the x. So I'm just going to do a bit of rearranging. We've got 5 to the x, which we're going to square, minus 8 lots of 5 to the x. So I've subtracted this now, and I'm putting this in the form of a quadratic equation. Plus 12 is equal now to 0. So if you want, you can go ahead and factor this straight off. 5 to the x minus 2, and then we're going to have 5 to the x minus 6 is equal to 0. Alternatively, you could now let p be equal to 5 to the x. So we'd have p squared minus 8p plus 12 is equal to 0. And we could write this now as p minus 6 multiplied by p minus 2 is equal to 0. So at this stage, we can say now that p would be equal to 6, p would be equal to 2. Therefore, now 5 to the x would be equal to 6, and this one we would say 5 to the x is equal to 2. And you would go ahead and solve using exactly the same method we've just looked at. This one right here, we can see that 5 to the x would be equal to 2, or 5 to the x would be equal to 6, and we would just now use logs to solve those. Okay, let's do another one. Let's go for this one right here. This is slightly different. So we've got here now 2 multiplied by 4 to the x plus 3 multiplied by 4 to the minus x is equal to 7. What I'm going to do now is let p be equal to 4 to the power of x. This one is slightly more, not tricky as such, but slightly harder to see. So what we have then is 2p plus 3 over p is equal to 7. So we'll just write this out. Multiplying through by p, we get 2p squared. Then I'm going to get minus 7p plus 3 is equal to 0. That gives us a quadratic now, and we essentially had now a hidden quadratic. So we'd have now 2p minus 1, and then we'd have now, what's that going to give me? P minus 3 is equal to 0. So all I've done is factored it. So what have we got here? 2p minus 1. That looks good on the factoring. That will be perfectly fine. So p will be equal to 1/2, or p will be equal to 3. We've let p be equal to 4 to the x, so we can say that 4 to the x is equal to 1/2, or 4 to the x is equal to 3. This one is quite easy to solve. If we just consider this one, this is going to be now that x is going to be equal to minus 1/2. That's just using the rules of indices. And then this one, we would simply say that x would be equal to log 3 divided by log 4. And we go ahead and evaluate that. So all I've done is taken logs of both sides, brought the power down, and written our answer like so. So with that one, just be a little careful. Okay, with this one's quite nice. What we've got, and I'm just going to rewrite this. I'm going to write this now as 2 to the power of 1 multiplied now by 2 to the power of 2y. And then we're going to have plus 7 lots of 2 to the power of y. Minus 15 is equal to 0. So if we look at this one, we could write this as 2 lots of 2 to the power of y squared. 2 to the power 1 is just going to give me 2. We've got now, using the rule we had before, we've got now 2 to the y squared can be written as 2 to the 2y. 7 lots of 2 to the y minus 15 is equal to 0. Again, if you don't want to factor that as 2 to the y, we'll write let p be equal to 2 to the power of y. So we have 2p squared plus 7p minus 15 is equal to 0. That's going to give me a quadratic, and we're going to have now, what's that going to be? 2p minus 3, and then we're going to have on here, what's that, p plus 5? Let's see if that works. That looks pretty good. Let's just check my factoring. 2p squared plus 10p minus 3p minus 15. So from here we can see that p would be equal to 3 over 2, or p would be equal to minus 5. Now let's just consider 2 to the y, so 2 to the y is equal to 3 over 2, or we've got this one now, 2 to the y is equal to minus 5. Now 2 to the y can never be equal to minus 5, therefore this is not going to give me a valid solution, and I'd make a note of that, not valid. Therefore we would just deal with this one and just solve for y. So take logs of both sides, make y the subject, and that will be fairly straightforward. And again, check they work. So all we've done is just use a little trick now and gone ahead and done that one. Okay, let's do another one. Let's have a go at another one. This one right here. 25 to the power of t plus 5 to the power of t plus 1 minus 24. So let's be a bit crafty. 25 is 5 squared. 5 squared to the power of t plus 5 now to the power of t plus 1. So what I'm going to write is this. I'm going to write this as 5 lots of 5 to the power of t minus 24 is equal to 0. So rewriting this, we've got 5 to the power of t, which we're going to square. So using rules of indices, plus 5 lots of 5 to the power of t minus 24 is equal to 0. Let p be equal to 5 to the power of t. So we're going to have p squared plus 5p minus 24 is equal to 0. That's going to factor nicely, 8 and 3, so we'll have p plus 8 and then p minus 3. That's equal to 0. P is equal to minus 8, p is equal to 3. Now if we consider that p is actually 5 to the t, what this is now saying is 5 to the t is equal to minus 8, or 5 to the t is equal to 3. 5 to the t can never be equal to minus 8. We've looked at that graphically, that's not going to happen. Therefore, all we need to do is solve for this one. So t will be equal to now log 3 divided by log 5. And I hope when I write that, you're comfortable with what I've done. I've just taken logs of both sides. Log 5 to the t is equal to log 3. T log 5 is equal to log 3. Dividing both sides to now make t the subject. T is equal to log 3 over log 5. And in the exam, I would show 4 workings. So that's a nice little one that we've manipulated to give us exactly what we want. Okay, let's just look at this one right here. We could just write this now as 3 to the x multiplied by 3 to the power of 2 and just bring that constant out. 3 to the power of 2. We could write this now as 3, in fact, I'll just write this and I'll split it up. This one is 3 to the power of 1 multiplied now by 3 to the power of 2x plus now 15, and then what we're going to have, that will be equal to 2 lots now of 3 to the power of 2 multiplied by 3 to the power of x. Just using the rules of indices, we know that if we're multiplying the same bases, we add the powers. So we could write this now as 3 lots of 3 to the power of x, which we're going to square, plus 15 is going to be equal to, we're going to have 2 times by 9, that's going to be 18 lots of 3 to the power of x. So if we just rearrange this, we've got now 3 lots of 3 to the power of x squared minus 18 lots of 3 to the x, and then we've got plus 15. At this stage, I can divide the equation by 3. So what we've got then is 3 to the x squared minus 6 lots of 3 to the x plus 5 is equal to 0. So if we let p be equal to 3 to the x, p squared minus 6p plus 5 is equal to 0. That leaves us now p minus 1, p minus 5. So p minus 1, p minus 5, and you know what you're doing from that point in. We've let p be equal to 3 to the x. With this one, we could simply write 16 as 4 squared. So we'd have 4 squared here, and then we would just go ahead and apply it. So that's looking at using logs to solve exponential equations. We've looked at linear equations when we've got an unknown on one side, an unknown on both sides, and now quadratics. So hopefully that's given you enough information to move on and answer questions like these.